So, welcome to this Danish IS lecture. It's a pleasure for me to present Benjamin Jäger. Benjamin has been at University of STU for a few years already, and before that, he was sorry about that. He was at University of ETH in Zurich, and today we'll talk about particle physics at the exascale and computing. Thanks, Benjamin.
Thank you, Francesco, for the introduction. Welcome, everyone. So today we'll talk about two topics. Like we have particle physics at exascale computing. So I'll naturally talk about both of these topics and we take them one by one. Of course, they are connected and interlinked, and that will hopefully come clear as well. So let me start with the first part, which is on particle physics. And let me directly hand over to Quantum Kate, who is our outreach mascot, and give her the opportunity to introduce the standard model of particle physics.
The universe is ruled by four forces. You know gravity, which makes things attracted to each other if they have mass. But there are also three other forces. The strong nuclear force, that through strong interactions between the quarks binds the protons and neutrons together in the nucleus of the atom. The weak nuclear force, on the other hand, forces things apart and can, for instance, turn a neutron into a proton, an electron, and an antineutrino.
Oh dear, not nice.
And finally, there is the electromagnetic force, the one with the photons that account for light, electric potential, and magnetism, and keeps the atoms in place. The four forces affect the particles in totally different ways. Let's try an example with an electron and a neutron. Gravity only affects stuff which has mass, and as the electron is nearly massless, gravity only affects the electron a teeny tiny bit. The neutron, on the other hand, is quite heavy and is therefore more affected by gravity. Get it? The electromagnetic force doesn't care one bit about weight. The only thing it cares about is electric charge, so it will go after the electron and is totally cold towards a neutron. The weak and the strong nuclear forces are turned on by totally different things, flavor and color. In the so-called standard model, you will find the known elementary particles which can be combined into hundreds of more complicated particles. Not just neutrons and protons, but also some that are called pions, kaons, and eta C, and lambda, and all sorts of weird things. And they are all affected differently by the four forces.
So thank you, Kate. So you have seen all the four forces and all the matter already, but let me quickly go through them. So like we have four forces, and in this talk I will focus mostly on the strong nuclear force. And as Kate was saying, the strong nuclear force affects color of particles. And we have, in terms of matter and forces, we have a distinction between quarks and leptons, and then the four forces like gravity, the weak interaction, the strong interaction, and electromagnetism. So when we think about the strength of different forces, like, of course, if you think about the name strong force, you would imply that this is the strong force and the weak is a weak force. And here are some relative strengths that you see here at the bottom. So like if we say the strong force is of order 1, then the electromagnetic force is about 1% of the strong force. The weak force is 10 to the minus 6, so a rather small fraction. So of the strong force, and gravity is, in this perspective at particle physics level, completely irrelevant, because it's 10 to the minus 45. The strength is so weak that it doesn't affect particles in that scale. And another interesting feature is, like if we compare QED, which is standing for the quantum electrodynamics, and it's for the electromagnetic force, there's a difference between the binding of the electron to the hydrogen atom is very small, 10 to the minus 8. For the strong force, however, this binding energy over the mass itself is very large, so 10 to the 2. So this is in very few orders of magnitude different. And this is also explaining why physicists have named this force the strong force compared to the weak force or compared to electromagnetism and gravity. So gravity seems natural because like we can feel it in everyday life, but the strong force, of course, is also like which makes up almost everything in the universe, and it needs to be understood. So there's one thing we can think about is like, how can we actually study those? And there have been lots of effort being made in the past, and is also currently made by building better and better particle accelerator. And the idea is very simple here. Like you take two things you know and smash them together and then study its contents. So if you take the analogy, you can take two cars and say you have an unlimited supply of cars and also don't have to worry about the passengers inside, then you can find out what a car is made of by crashing them together and analyzing the products that you find afterwards. So of course, this is very big effort because like it's quite a bit detective work to study what comes out and then reassembling what was in there. But this is effectively what's going on right now at these big collider facilities. They collide two known particles and study what comes out at the end. And from this, they reinfer what actually made up matter in the first place. So this is when we look at these big machines, like these are pictures from the Large Hadron Collider in Switzerland, where it's basically a tunnel of 28 kilometers circumference. There is where we have these particles, and these are collided inside these big detectors, which is shown in the picture on the right. And if you look careful, you can see a person standing at the bottom. So to give you a scale. And then if you take the analogy to these car crashes and studying those, then you see a picture of these accidents or car crashes of particles here on the left, on the bottom. And you can see like after they're smashed, a lot of things come out and they have to be carefully reconstructed in order to find out what was inside and what made actually matter. So you can imagine this happens like a million times per second. So this is quite a big challenge to analyze these results. But since this has been going on, this search for decades or even longer, people have a good understanding what actually makes up the universe. And this is also where we come back to what Kate was introducing, the standard model of particle physics. So we have different things that build everything around us. And this is as far as we know, everything we know as of yet. Of course, in the future, there could be more, but right now we have effectively 6 quarks, which are shown here in purple, 6 leptons, and 4 force carriers, which are here in red. So like we have for the strong force, the gluon, and for the electromagnetic, the photon, as well as the W bosons. And more recently, you probably heard in the news about the Higgs boson, which is responsible for some of the mass in the particles. The things you might have heard is like basically electron up and down quarks, which make normal matter, like me, the laptop, and everything around us. The other things are basically heavier copies of it. And it's an interesting question, like why they arise and where they come from and what they are made of. But nevertheless, there's many things to be still studied. As I said, here we'll focus on the strong nuclear force. And when we think about this strong force, then actually 99% of the proton or of atoms or of us, of me, you, are basically this, made out of the strong force. Not made out of quarks, and these quarks are bound together by the strong force. And this is what makes 99% of all of the mass. And this is quite a big fraction. So we need to understand that carefully in order to make good predictions and understand what we're made of and what things are combining. In principle, the strong force is a rather simple theory. You can write it down in one line, and it's only here shown for illustration, so you don't have to understand that. But it turns out to be actually very hard to solve. So if you try in the usual ways, you actually fail there. So we still struggling to get a good insight into how the strong force works and how it does deal with it. So this is what I summarize in the bottom, like saying, well, it's still the source of many uncertainties and unknowns. So especially like if we look back at these collider experiments, the main uncertainty driving what comes out of this in our understanding comes back from our understanding of the strong force. So there needs to be some better ways. Let me quickly explain how we normally would solve this theory or understand it. The idea normally would do is like, well, we do a Taylor expansion, or like which for physicists have developed these Feynman diagrams. And this is just an understanding, well, how things combine and how things react with each other. So formally, this will be in Taylor series, so we can expand our problem into smaller and smaller things, and then construct a theory. Unfortunately, it turns out for the strong force, this expansion coefficient we normally have is of order 1. That means we would have to take this series to infinity. That means we have infinitely many of these diagrams to compute. And this is in practice as well as theoretically impossible. So we have to work in different ways. And the method I use more specifically is using so-called path integral formalism. And the idea here is also simple. Like the idea is to integrate over all possible paths we can construct between a point A and a point B in space-time. And then just, well, as I said, just integrate over them. And if I write that down formally, like we have something which we call position function Z, and this is just an integral over all the possible paths we can find. But if you actually write this down and try to solve this, this is mathematically not well defined, because what we need to do here is we have to take infinitely many integrals. So we don't know anything about their convergence or even if they exist. So this is mathematically not well defined and a nightmare. So we have to do something simpler for that. And one way to address this is to look at a discretization scheme. So like instead of using continuous time, we say now our space is made out of a lattice grid. So we have points that are separated by this lattice spacing A. And if you do that, our integrals become finite. So we still have to take integrals, but like we have to only take n integrals. There might be quite a few, depending on how many points you use in order to discretize your space and time. But in practice, it's actually just in quotations a normal integral to solve. And that is something we can do rather straightforward. So we can use numerical techniques to solve this integral explicitly. I know it's a very high dimensional integral, but in principle, there's nothing preventing us from this. So when I look a bit about like, okay, how many integrals do we actually have to do? So like about the dimensionality of this integration. And this is an integration that in state-to-the-art calculations these days is of the order of a billion dimensional integral. So we have to take say 1 billion integrals to solve this. If you remember from high school or early university studies, like we can, of course, let's have a function like this. We have an arbitrary behavior, and we can do this numerical integration by just putting, say, 4 points, and then trying to estimate the area under this curve by using these trapezoidals. But if you look aloud, if you want to do that in 1 billion dimensions, then actually, well, you have to solve 10 to the 600,000 integrals to compute. And even with today's computer, this is impractical. That would take you more than 1 million years to do anything close there. So this is also not a practical solution. So we are still struggling with these high dimensional integral, and the usual or simple approaches are not working. And luckily there's a way to deal with this, and this is known as Monte Carlo integration. So what Monte Carlo is here indicating is that we use random numbers, or like you do in a casino, rolling dice. And there's a picture of the city of Monte Carlo, which this method is named after, and of course some dice in a casino. And let me give you a small example. Like let's say we want to find a number of the number pi, which you probably have encountered before. And this can be done easily by throwing just random numbers or throwing darts at a 2x2 box, which goes from -1 to 1, which is shown here on the bottom right. And then we can approximate this number pi by just counting how many darts here in red are inside the circle and over the total number of darts we threw into the square. And this is now a numerical integration technique in 2 dimensions. But interesting enough, this technique can be extended to arbitrary high dimensions, and for our case, even a 1 billion dimensional integral. So let me show you how that works in detail. So let me just try to shift over to a small applet to show how this works. So like this is, as I said, like the start exercise. We have a circle in the middle, and we're trying to throw a few points. And then what we will see here is how the estimate of pi, which is, we know the number, of course, is shown here in the dotted lines, will improve of how many points we use. So like say we will throw 1 dart, 2 darts, 3 darts, and so on. And I will just go over to this website, which is a nice illustration of this. It should take a second, and then we'll see, okay, we started, we're throwing some dots. I hope you can see some. I stopped it now. We have thrown 31 darts and 28 landed inside. So that means we can build the ratio of just 26 over 31 and have our estimate of pi. And you see, like, it is still a bit off, but like our current estimate is at 3.35. And if I keep it running, it will improve. Of course, because it's a random process, it will fluctuate around. But if I increase the number, so like we started here at 10, there's 100, so there's a logarithmic scale, then 1,000 points. You see we're getting better and better, getting closer and closer. And this is the basic idea behind Monte Carlo integration or Monte Carlo simulation. We're using random numbers to trying to solve an area problem. And now we have almost close to 1 million points. And now the estimate seems to be pi 3.141, which is more accurate than a percent or per mil even. So this is the idea that goes behind the Monte Carlo integration. So I should go back to my presentation. Which I quickly have to switch back. And continue. So this was the idea we want to use. So in order to solve our big problem or numerical problem, which comes from this path integral formalism, we can boil it down to doing a numerical integration just using random numbers to trying to solve. And this all goes back to this Monte Carlo method of trying to throw darts into an area. So what this field, what we do is like Lattice QCD, and this is, of course, trying to solve problems in particle physics. And we, of course, we use here technology from techniques from applied mathematics, and we, of course, will combine this with high-performance computing. And my research, in more particular, will actually go on to looking how the strong force, or QCD in this case, behaves as temperature and the density is changed. So this is a prediction that we looking at. So like we live round about down here at where there's 1. I'm not sure if you can see my cursor, where all these 2 lines start in the hadronic phase. But we know we want to learn a bit more about the early universe. And we know the early universe, everything was very hot and very dense. So we need to understand how the strong force behaves if we make things hotter, if we make things more dense. And this is a phase diagram, so a function of temperature and density or pressure. And you can think about like the analogy which you might remember from school for water. So if I look the phase diagram for water, in instance, like water freezes at normal pressure at 0 degrees. It boils at 100 degrees, so point B and C. But of course, this changes if we increase the temperature or decrease the temperature. And in order to map out these lines, this is what we want to also do for the strong nuclear force. And this is what this diagram effectively is showing. We predict some line separating these two different phases, and there's many very interesting phenomena here that we are interested in. And maybe something to say about like the scale of these things, like we have here temperature, which we measure in 100 MeV. If you convert that into something more common, like in Kelvin or Celsius, it doesn't matter. This is 10 to the 12, so it's a huge temperature compared to everyday's life. And also the densities we're talking about here are 10 to the 17. So this is a 10 with 17 zeros per kilogram per cubic meter. So these are densities which occur in neutron stars or other astronomical objects. So this is what my research is aiming for. But as I said before, we're trying to do computer simulations, and like we want to do that. So what I'm trying to attack this problem is like, okay, trying to simulate here at this line, trying to expand into this direction, and also with a different method, trying to simulate directly at different points. So this is from top to bottom. We see these red dots, the green lines, as well as the blue dots were the indication for simulations, which I'm actually doing right now. So when we talk about simulations, then we also should mention, like, going back to my title, I said like particle physics. So I gave you a bit of an overview, a bit into depth at the end on what I'm interested in terms of particle physics. But there's another problem when we talk about computing, because we want to do this, remember these integrals we were talking about on a big computer, and we need to do a billion integrals. So we need to have fast computers. And computers are evolving every more and more. These days, we are getting closer to what we call exascale computing, and I will explain what that means. So first of all, give you an idea what exascale computation is. And like, if you look at the definition, this is computation. So a computer that can compute with at least one exaflop. So it has at least a computing power, which we measure in floating point operations, so flops. And one flop stands here for floating point operation per second. And then one exaflop, exa stands shortly for 10 to the 18. This is 1 with 18 following zeros as operation per second. So you can imagine this is a massive amount of computing power. But of course, we need to relate this in order to understand this a bit more. So what means a flop? So like if you take an example, like here multiplying these two numbers, 3.14 times 2.71, this is one operation. It's a floating point operation because there's a decimal. So this operation is one of these operations. So if you think about yourself, a human is capable about one floating point operation per second. That is if you're very fast. So in order solving this multiplication, you have 1 second. Then you as a human would have one flop. You can do one floating point operation per second. And again, these days we're looking at computers that can do significantly more. We're talking about exaflops of 10 to the 18. So let me show you again this huge number just as a reference. So you can imagine you need a lot of humans in order to even get close to that. And that's not going anywhere. Quick word on precision. So because computers don't do exact arithmetics, we only do approximate arithmetics. We have to deal with some precisions, and you might have encountered these as 32 bits or 64-bit computations. And this only means that we have only a certain number of precision. So in the case of a single precision, we have about the order of 6 significant digits. For double precision, about 15 significant digits. And in the scientific community, there's only double precision being used, so like 15 significant digits. So when we talk about some time ago how a computer evolved, and this is just as a reference, like we had, for instance, 1,000 floating point operations in the year 1973 for the first commercial CPU. So this was in Intel 4004. Then going to 1 million operations per second was reached a couple of years later by the processor made by Motorola. Then we're going further, and like this is probably the area when people remember, like when we talk about gigafloating, so 1 billion operations per second, and this was achieved in the year 1999 by the Pentium 3 processor, which some of you might even have had in your computer. Then more recently, like in the year 2009, the first graphic card was able to reach a teraflop. This is a trillion operations per second, or 1 million times 1 million operation per second. This is a single graphic card being able to sustain this amount of computer power. Then going a factor higher, 10, so petaflops, this is 10 to the 15, or 1 million times 1 million times 1,000. This was a 2013 state-of-the-art supercomputer. So about 7 years ago, this was what people were using at the maximum. Right now, we're going into the area of exascale computing. That means we have the first, or very soon we'll have the first machine that actually can compute 10 to the 18. This is 1 million times 1 million times 1 million operation, or 10 to the 18. And this was first achieved in single precision for the supercomputer, which was built in 2020, being made available, and this is a Japanese supercomputer. At double precision, so for scientific computing, this roughly operates at half the floating point, half an exaflop. And maybe just a quick remark here, a supercomputer is typically that is built out of more than one single processor, typically of the order of thousands of, or tens of thousands of processors. Maybe one word about phones or current mobile chips. Like even if you think about your phone, which you have in your hand. So these are the most recent chips from Apple and one of the Android providers, and these are operating at 800 gigaflops, close to a teraflop operation. So a single phone has right of now like the possibility to do 1 million times 1 million operations. And nevertheless, here for reference, exaflop is still 1 million more. So you can imagine. But if you go back to the history overview, like saying teraflops, these were supercomputers about 20, 30 years ago. So right now, our phones have the same computing power as supercomputers had like 20 years ago, 15 years ago. And this is all driven by, of course, the technology advancements in computer technology. And very interesting enough, there has been an observation or prediction made by Gordon Moore in 1965 even, and he predicted that the number of transistors on a microchip will actually double every 2 years. And it is interesting that this trend, he was expecting it to hold for 10, 20 years maximum, and it is still quite accurate these days. Of course, there is no clear translation between number of transistors to computational power, but the number of transistors is a good approximation to how much computer power is available. So it's sometimes more publicly referred as like the computing power is doubling every 2 years. But technically the term he used was transistors. And if you look at how this actually was going, so here's a timeline from 1970 to 2020 with the processes that were available or how many transistors they're actually using. And this is a logarithmic scale. So doubling would be on a straight line. And what we can see, even looking by eye, even over the wide variety of 50 years of computing time, this trend has continued. And even to these days, which are the top right corner, and if you can zoom in into these, you can see computer chips which are currently produced or currently made. So these are actually still having this trend, more or less. So this trend seemed to continue even longer than people expected it to do. Maybe something about how supercomputers actually made up. And here's a diagram showing how these are built up. And this is an old supercomputer from 2009, but I think the illustration still is about right. So you have chips, and you build these chips into modules, and these cards, you stack them into one node card, and then put many node cards on top of each other, and then have multiple of these racks. And then, of course, interconnecting them and switching them together, you can actually have a supercomputer which is able to perform these insane speeds we were talking about. So right now, the best computer in the world is the Fugaku supercomputer, which is half an exaflop. So there's even a list maintained, which is called the top 500 list. It's being published every half year, and it lists the top computers in the world. And as I said, here currently the first rank has performance, which is here highlighted. It has 7 million cores, so 7 million processing units. And the performance in total here shown by our peak, which is in teraflops. So this is half an exaflop. Of course, also you can see this consumes about 30,000 kilowatts of power, this machine. And then, of course, this is the current leader, but there's, of course, a second one which is at smaller scales, but like still a massive computing power. And you can find more details on how the machines are made, because there's not one unique way to build your supercomputer. And each provider designs differently and how to build them. But just this is the state of the art. So we, of course, have it was published in November 2020. There will be an update in June 2021. But as far as I know, currently the Fugaku supercomputer is still the #1. So when we have these big supercomputers, it's not straightforward to even use them. And there we come into problems like, how do we use them, or how do we do our coding for this? Normally, when we do software development, develop code and trying to solve problems, in my case in particle physics, in other people's cases in other areas, well, you're trying to have a problem and trying to split up into very basic operations. For instance, I'll do this, multiply this, do that, and so on. So it's here schematically shown as like we have our problem, we dissect it into many, many different small biting blocks, and then give them to a processor to operate on that and execute this. But of course, well, this is what we call in serial. So if you have only one processor. But these supercomputers as its own have about 1 million or a couple of million cores, so we have to think about differently. So when we talk about parallel programming, so we want to, then we have to think about that we have to dissect our problem into 4 sub-problems. And then each sub-problem has to be divided into bit-sized problems in order to be solved on each processor. Or maybe make an analogy. So like if you talk about parallel programming, make the analogy of a big field. So like we have a big problem to work on, so a big compute problem. And then the idea is, well, we divide the field into, say, 4 fractions, and then each worker, in this case a processor, will work on each field. And of course, if necessary, they communicate and exchange data whenever necessary. And in the end, they bring all the result back into the barn. So this is how, in principle, we divide up our problem. So we have a big problem, then divide it into smaller sub-problems, and then let 4 people, in this case, work for farmers work on these fields, and then give the result. This, of course, works very simple if you have, say, a couple of workers. So I easily can probably manage to organize 4 workers to organize, okay, you do this, you do that, you do that, and whenever necessary, we have to exchange information, sort out what needs to be done and what's left to be done. But even these days, normal chips have thousands of workers, or supercomputers even millions of workers. For instance, for example, if you have these more recent chips from developed by NVIDIA, this has 3,000 cores in double precision and about 7,000 cores in single precision. So in this case, you need a very big problem that can be separated into much, much smaller, tinier problem. And you still have to organize these workers into smaller blocks in order to be feasible. And you might wonder why I show you here a graphic card or graphic chip. And this is because graphic cards have become very, very powerful because their development was driven by gaming, and then they recently have been made available for general purpose computing. So you can use your graphic card, which normally does your computation, to do computer games, to do scientific computing. And this is what we are interested. But of course, this requires, here's a small sketch shown, like we have, of course, still our processor in our memory, and then we have one or two graphic cards, and they have thousands of processors, so we have to organize them and have to tell them what to do when and how to communicate forth and back. So this, in terms of our field analogy, requires even more organization effort, because we have to think about which worker does what, at what time, and when to communicate intermediate information and exchange information. But nevertheless, it can be done. So this is actually what right now my research is also involving into, and this is basically to port our current simulation code, which we use, as I said, for these simulations, which I showed for the particle physics problems, which I showed before, to make use of graphic cards. And of course, this requires to think about how these work, how we can optimize these, and how to get these thousands of workers to work efficiently and work on our problem. And this will be a necessary step in order to make our simulation ready for what we call the exascaling area. And for that will be supported by 3 different grants, or three different support units. And this is an Irish high performance computing grant, a UK grant for extreme scaling, and a partnership for advanced computing in Europe. But this is something which will need, in order to be up to date and being feasible for the future, this is something that has to be done and currently investigating. Of course, there's also other developments which might be very interesting, but this is still the future. And this is what we talk about in terms of quantum computing. And quantum computer could be a big, could provide a big change, because a quantum computer provides a completely different way to do certain computation. In our classical way, so this is shown on the left, the classical bits, we only can have 0 or 1. We can only have power on or power off. Interesting enough, quantum systems can have an intermediate, so they can have on, they can have off, and they can have both at the same time to some degree. And these superposition, as we call it, these being in a state of on and off simultaneously, can be used for computations very efficiently. And these days, first prototypes and first small scale quantum computers are being constructed and developed. So this might be a new change in the future, but still there's even more efforts necessary, because new algorithms and programming need to be developed in order to be able to use these quantum computers. And also new problems occur, because these quantum computers only work efficiently if they're very, very cold and left alone effectively. But of course, in our environment, we cannot achieve very cold environments and left alone environments. So we need to work on something which is known as quantum error corrections, in order to, if a fault in a computation occurs, we know about it, because in classical computing, these faults occur, but these are so unlikely or so happen so rarely that we don't have to worry about those. They occur on average every thousands of years. So there's nothing to worry about. But with quantum computers these days, they occur about in every second, say, operation. So there's something we have to be worked on. And that's, I think, all I had to say about particle physics and exascale computing. Like you can see that these work very hand in hand, because we have problems in particle physics that are to solve billion-dimensional integrals in order to understand one force, with a strong nuclear force. But on the other hand, also like to develop codes that run efficiently on supercomputers or even smaller computers is a challenge in itself. And I think this is where my research area goes into. It is directly in the middle and combines both of these approaches. So I'm trying to optimize or trying to develop algorithms or methods for that have an application in particle physics, but also to understand or like to manage these simulations at exascale computing or at soon exascale computing. But with that, I would like to thank you all for your attention and be happy to take questions